Hi, I'm Dennis Veller, and this is the Reiki Tube Lab Report. A Reiki tube is a pulse combustor. In a pulse combustor, combustion intensity oscillates sinusoidally, like a sine wave, which drives pressure and velocity oscillations within the combustion. If the heat source is positioned correctly and the injection of fuel is timed correctly, then this oscillation will be self-reinforcing and will generate a standing wave. This is resonance. Pulse combustion has many interesting properties. It leads to increased combustion intensity, increased fuel mixing, and increased heat transfer to the wall. That last thing can be beneficial in some situations, however, can be an engineering challenge in others. Pulsed combustion also serves to push exhaust products out of the exhaust. Here is the experimental setup. You can see two pictures of the experimental setup, and the different components are marked on the pictures in red. The first component is the methane burner itself. The burner platform position can be adjusted, and we did this for parts of our experiment. The second component is the photomultiplier. It measures combustion intensity by measuring light output at specific wavelengths. This photomultiplier is measuring the output at the wavelengths corresponding to the output of glowing OH radicals, which are produced by combustion. The third component are piezoelectric pressure sensors. 3 of these are attached to the tube, but they are removed from the chamber wall as they are very sensitive to temperature. The fourth component is the valve. This valve allows us to open the tube out to the environment and disrupt the resonance. Here is our experimental procedure. Pressure and photomultiplier data, along with qualitative observations, were made at various times. We first observed when the burner was at the 0 position, which is the optimal position for resonance. Then we opened the valve and performed observations again at the same position. We then closed the valve and performed these observations at the 2 inches position. Finally, the burner was raised until the resonance stopped. Observations were performed at this point. This was at 5.6 inches. The burner was then lowered until the resonance resumed. This occurred around the 0 condition. You can see the final few seconds of the burner being raised and the resonance stopping earlier. As you can see, for the sake of this canned format, the video is also on the screen again. Here are the results of our experiment. At the bottom of the slide, you can see the data that we have collected and analyzed for this presentation. We present the frequencies of the oscillations observed by the various pressure sensors in the various conditions, along with an estimated resonance frequency. We present the relative phase angles of the oscillations of the different pressure sensors and of the photomultiplier in the 0 position when the valve was closed. We also present the root mean square pressures in decibels of the various pressure sensors in the various positions. Finally, we present the various photomultiplier data. We present the root mean square voltage measured by the photomultiplier, which corresponds to the intensity of combustion, along with the frequency of the oscillations measured by the photomultiplier. Note that only the first one, at the 0 closed position, has any significant meaning, as at the other positions the photomultiplier was no longer aligned with the flame. Qualitatively, we observed that resonance was immediately lost when the valve was opened, as this was no longer flame in a sealed tube, but just open flame in an environment. Resonance was also lost when the combustor was raised 5.6 feet above the 0 position. Resonance only returned when the combustor was very close to the 0 position. Here are the answers to the supplemental lab questions. A photomultiplier tuned for a different set of wavelengths would not work as intended for this lab. The photomultiplier we used, as stated earlier, is tuned for the specific wavelengths that excited OH produces, a radical that is produced in combustion. Measuring a different set of wavelengths would simply not have the desired effect. The experiment would still work with hydrogen as fuel, but the amount of fuel would need to be adjusted as propane and hydrogen have different densities and different energy densities, meaning that injecting the same amount of fuel would not necessarily have the same optimized impact on the pressure oscillations. Finally, a tunable Reiki tube could be made by adding another gas into the tube with a different molecular weight and therefore a different specific gas constant and a different specific heat to change the speed of sound within the tube, thereby changing the fundamental frequency, which is the frequency of oscillation. For our conclusion, we'll return to the idea that pulsed combustion can lead to more intense and therefore more efficient combustion. This can be seen clearly in the photomultiplier data. In the resonant case, the photomultiplier measured very intense, and therefore very efficient, combustion at 97 Hz. In the non-resonant case, there was no peak of intense combustion. This indicates that in the resonant case, combustion is more efficient, as there is very little of that lower intensity, lower efficiency combustion that is present in the non-resonant case. Pulsed combustion therefore could have applications anywhere that fuel efficiency is a concern for combustors, and of course noise is not, as pulsed combustors, by their nature, are very, very loud. This could be industrial applications or in rocketry. For example, rotating detonation engines, though working on a completely different physical principle, are somewhat analogous to this. in that they induce a very, very intense, not even a combustion, a detonation in their case, but still a very, very intense pulsed reaction. Note that because of the noise issue I mentioned earlier, pulse jets are actually not a very realistic application of pulsed combustion, even though it was one of the earliest applications of pulsed combustion. Well, thank you for your time.